In this video, I'd like to talk about the math question of the day for Friday, June 16th, 2023. And with this problem, we need to find the distance d between these two complex numbers, z1 and z2. And finding the distance between complex numbers is often taught in a pre-calculus class. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through it. And we just need to find the distance between these two complex numbers. Now, we could use a version of the distance formula, but I do find that it's helpful, at least when you first start learning these, to draw a picture. So let's draw in the complex plane, and we can plot both of these points. And with this complex plane, the vertical axis is the imaginary axis, so this will go up in multiples of I. And our horizontal axis, that's our real axis. These are just the real numbers. Now, the scale that we can use for this plane, we can go by 2. So this could be 2, 4, 6, 8, and so on. Likewise, we have for the negatives. And for the imaginary axis, we can do multiples of 2i. So 2i, 4i, 6i, 8i, and so on, likewise for the negatives. And let's plot this point, z1, this complex number, at -9 minus 14i. We'll do that in green. So we need to go left 9 units on the real axis. And again, we're counting by 2, so that would be right about here. And we'll go down 14i units. So since we're going by 2, we'll just count out 7 of these. That's 4, 5, 6, 7. So right there. And we can meet right about here. So this point right here, that is z1. And we'll plot this next point. We can do that in the pink color. This z2. We go left 2 for our real axis and down to 13i. Or minus 13i for our imaginary axis, which is right about there. So that point is roughly right there. We can call that z2. Now, what we're trying to do is find the distance between these. So we can construct a line, and we call the length of this line d. And the general strategy, if we're not using the formula, is to deconstruct this into a right triangle. We can draw a line that is parallel to the real axes, going from the green point here to the pink point here, but it is, again, parallel to that x-axis. And we'll drop a line that's parallel to the imaginary axis from z2, going downward, to the y value of z1. So we get this right triangle, and essentially we just need to figure out what the legs of the triangle are. And from there, we can use the Pythagorean theorem. So let's focus on the real values. We know z1 has a real value of -9. Let me get off the line tool there. And z2 has a real value of -2. So if we find the difference of these numbers, or we can just count it out, that would be 7 units. So the horizontal component of a right triangle is just 7. And for the vertical component, we know that z1 has an imaginary component of -14i, where z2 is at -13i. So that is just 1 unit apart. And since we're dealing with a right triangle now, we're just talking about the distance between them. So we can drop the imaginary unit, since that really just tells us the direction. But this vertical component here would just be 1. So let me redraw that triangle. We have a right triangle, like I mentioned, and it's not perfectly to scale anymore. Well, it was never perfectly to scale, but we can draw in a rough approximation here where the vertical component is length 1, the hypotenuse is length d, and our horizontal component is length 7. So we can use our Pythagorean theorem, where we take our legs, we square them, and we add them together, and that's equal to the hypotenuse squared. So let's set it up for our triangle here. We would have 7 squared plus 1 squared, and this is equal to the hypotenuse squared. And if we simplify, this is 49. This is 1. We are equal to d squared, so we have 50 equal to d squared. And we can just take a square root of each side to simplify this so that d is the square root of 50. And usually when we take a square root of each side, we would have to put plus or minus, but we're dealing with a physical distance here, so we just have the plus rather than the negative solution. And we could actually simplify this further, since root 50 can be split up into the square root of 2 times by 25. And if we separate this product into their own square roots multiplied together, we can actually take a square root of 25, that's just 5. So root 50 is 5 times by the square root of 2. So this right here would be our fully simplified final answer. Now, like I mentioned, we could also use the distance formula to figure this out, and I will paste that in just so that we can see it. So this formula right here, this is equal to d, this is our distance. But this is exactly what we did, except in our case we had z2 and z1. So we find the real parts of z2 and z1, we find their difference, we take the absolute value and we square them. So in our case we had -9 and we're subtracting -2, so adding 2, which would give us -7, but we take the absolute value of that and then square it. That's our 49 here. Then we do the same for the imaginary parts. We have -14 minus -13, which would be -1. And then again, we take the absolute value of that, which is +1, and we square it. That is this part right here. And our equation was equal to d squared. This is d is the square root of this. We could just square each side to get back our d squared. But from this formula, you can see that we basically used it, though we took a longer approach. We drew out a picture. And the picture gives us intuition for why the formula is true. This formula is really just the Pythagorean theorem used on the complex plane.